Okay, hello everybody. Can you hear me?
Yes.
Okay, thanks for confirming. Okay, now I see that right after we open this session, I see that you are all joining in fast. So I thank all of you for joining this session. I'll just say a couple of words just so that we can give more time to more of us to join the class. And in case something goes wrong with my microphone or you cannot listen to me, please just raise your hands. Hello. Yeah. Whenever I've done this before, I always say that remind each other not to leave the microphone open. But when I say that, I mean it. I include also myself. Okay, so if in any case my microphone is closed or it's open unintentionally, remind me, but remind also each other. So during this session, it is strongly suggested to keep your cameras off because the bandwidth might not allow all of the information to go at a good rate. And in the meanwhile, I can also try to set up for better quality streaming. I think we are good. Okay, so again, I'll just shut this down in a second. And you won't see me much, so please them now. Entire screen. Okay, I just want a confirmation from you telling me that you are seeing my screen.
Yes.
Okay, so then we can start, I hope. So okay, I guess some of you might join a little later, but even if they do, this session will be recorded. So since this is recorded, I need also to tell to you that you are being recorded. So in case you have any at least you have to know about it. So some beautiful questions that you might be asking, you'll be able to listen to them again. But at the same time, you might opt for having good control of your microphone. Okay. So first of all, I thank you for joining this session. It's really so we had in the first week we had an introduction of overall of what this course is about. So I hope that part is clear. But in case you have any further question, please don't hesitate to send me emails regarding all aspects of the course. Also, we are using Google Classroom because it provides all these nice facilities of or all these nice platforms where you can log in and you can connect to streaming live videos or similar types of communication that we are holding together. But at the same time, since Moodle or LMS is like your second home, I'm also uploading a couple of materials there for a few reasons, which I can explain them in length. But I'm assuming that you are comfortable with LMS. So once in a while, you can have a look over there, and some useful materials, I can put them there. With this said, I have also posted one video, which is on YouTube, with the exact link. So you could go to this video that I put together. There are a couple of examples where we use Taylor series expansion, and I guess maybe it's time for me to go a little further. And you can have a look at that video. And if you have any questions, of course, you can come back to me, and we can move on with the material. And can I have a confirmation? I guess you are seeing my PowerPoint presentation, right? I think this part, can I have a confirmation from you? Are you seeing my screen?
Yes.
Okay, thanks. Thank you very much. Okay, so we started the course where we by stating that we use some interesting mathematical apparatuses that are very useful to make clear a lot of concepts. And one of those, the most important, one of the very useful concepts is the idea of the use of Taylor series expansion. I'm sure all of us, we take this one in the first course of calculus. It looks a little trivial sometimes. It looks a little complex at a different, when you switch to a different chapter or a different topic. But all it becomes very useful when you come here in numerical analysis. And the most used mathematical apparatus or trick that we use, that we learn in calculus, is the derivative. So we are going to see this derivative a lot, and it's pretty obvious. The Taylor series expansion, it looks as it's written here on the slide. In order not to switch from video and to the PowerPoint, I just put some handwritten notes here. So as you can see over there, we take an infinite number of derivatives of a function, including also the zeroth order. This much, that's what we do. We try to expand the function around some point x0 to evaluate the function at some other point. But using the capabilities of, no, maybe I think I can continue in here for a second. I just wanted to switch from the PowerPoint to the video, but since we are here, probably what Taylor series expansion does, it just assumes that for any function which has any specific behavior, we can use, so we can expand using the values of a function evaluated at x0, which in this case the value of the function at x0 is this point here, which would be the f of x0. This is the y, this is the x-axis, and then we want to find the value of the function here at x1 using everything given for this point x0. So the given, always in any equation or in mathematics, in principle, we always have to figure out what is given and what we need to find. What is given for us, which is the value of the function f of x0, is going to be the first derivative of x0, the second derivative of x0. So this is a given, okay? and goes on. Then what is to find for us is to find the f of x1. Okay? So this is the question. And the idea is that the zeroth order approximation for f of x1 is equal to this actually. So using only the zeroth derivative, the zeroth order approximation is that what is this f of x1? This is the question. We say that the f of x1 is equal to this f of x0. F of x1 is equal to f of x0. This is the zeroth order approximation. As long as the x1 is far away from x0, the errors might increase. But now we say that let's try to approximate to get a better approximation, because it looks like we have some error which is shown here. Okay, and in order to do this, we first identify what is the first derivative, because in the Taylor series expansion, to get a more precise result, we know that this is going to be plus the first derivative of this function evaluated at x0 divided by 1 factorial times x1 minus x0. Now to find the derivative here, you know that it's going to be a slope that is going to look like this. But then this slope, it's a little extreme. If we follow this slope and we use the first term we see here, the next approximation is going to be a point here, which looks like the error is going to increase much more than it was. But then if we include the second order expansion, which includes the second derivative of this function divided by 2 factorial times x1 minus x0 squared, we hope that this error that is here, we hope for it to come somewhere down. Okay? So this is what we want, what we want to see, or we want to do with the Taylor series expansion. We're going to see this one used a lot in the root finding, because in the root finding, the idea or the use of the derivatives, it will become very obvious. I guess These were also in the previous video, so I might skip these slides a little fast. So this is how we try to approximate a function which is the cosine of x. And the function of cosine of x, it has an infinite number of derivatives, so we can always take derivatives out of it. And which is, of course, a lot different from polynomials, which have polynomials which are of the nth order, or polynomials, say, when n is equal to 5, we would say that the polynomial of fifth order has a maximum number of derivatives that you can find before you get a 0. So this is the few orders of expansion for the cosine x function. You can see also how we calculate the error. So in red color, what is shown in this slide, we can see that is that the total error. The total error, it is defined as the true value minus the approximated value, which in this case is 0.7071, divided by 0.5, which is a true value. And in this case, we say that this is a true value because we're trying to approximate the cosine of pi over 3. Pi over 3, in radians, it's 3.14 divided by 3. But at the same time, in degrees, where some of us might be more comfortable to talk about, pi over 3 is 60 degree. 60 degree, the cosine of 60, it's 1 over 2, so it's with infinite precision, we know that it's 0.5, but then using the Taylor series expansion, the first approximation, it tells to us that this cosine, it could be something like 0.7071. And we figure out that with respect to the true value of 0.5, the error is something like 41.4%. In the first order approximation, we approach closer to the exact value of 0.5, we get 0.52, then one further, we get 0.4979. Sorry, what was it? It's 4979, yes, correct. So I try to show this one also in this drawing here. So the zeroth order approximation, it's going to be the cosine of pi over 4. We know how cosine looks like. At 0, cosine is 1. It progresses to a further pi over 2 in the x-axis. We get a 0. It's an oscillatory function. It's a smooth function. A smooth function, that means that it's a differentiable, and it's a nice thing to work with. Now here we can see another example here. And I guess this drawing, which is in this slide, does not have all the calculations, but no, I think it does. No, it does, yeah. So we have a linear function, which is 3x plus 7. And we are using the same idea, we are using the same points, which we showed in the previous cosine example, just that we notice that we have only two terms to consider. If you compare, and it's a nice thing to work with. Now here we can see another example here. And I guess this drawing, which is in this slide, does not have all the calculations, but no, I think it does. Yeah. So we have a linear function, which is 3x plus 7. And we are using the same idea, we're using points, which we showed in the previous cosine example, just that we notice that we have only two terms to consider. If you compare, and it's a nice thing to work with. Now here we can see another example here. And I guess this drawing, which is in this slide, doesn't have all the calculations, but no, I think it does. We're having an undesired echo here. So I was hoping it could be that it's gone. Probably this is something some of you maybe try to, I'm not sure how it happened. I have a couple of theories, but let's go on. So there was my sound repeated again. I hope you can hear me. If my voice stops, please raise your hand. So let's move on. So this was a linear function. Now, when you have these linear functions, what we are doing with Taylor series expansion, in principle, by just picking up just the few first terms to approximate a function, what we are leaving out that in English language it means truncation. So we're just cutting up some part, assuming that this is very small. Now, these parts which are presumably small, they are, if you have a look at the Taylor series expansion, you're talking about terms that you're throwing away, which look like x1 minus x0 to the power n. If we are too close to the x0, assume that the delta x is something like 10 to the power minus 2 or 10 to the power minus 3. A square of that means that you get a 10 to the power minus 4 or 10 to the power minus 6. A cube of that means that you get a 10 to the power minus 6 to 10 to the power minus 9, which is some epsilons or some small values, which you can truncate them out, you can take them out. But there is another issue when we discuss the total. So we have the step size that you see in this graph. It can be the first impression, it would be the following. Let's try to decrease the delta x, x minus x0, as much as possible to decrease the error. But that's not always the best thing to do, because we have two competing terms when we are trying to calculate the overall error. We have the truncation error, which decreases by decreasing the step size, which means that if we have a delta x of 10 to the power minus 2 versus delta x 10 to the power minus 4, the 10 to the power minus 4, it's way better, because the square of that would produce a 10 to the power minus 8, which means that we are talking about relatively small errors. But as we are decreasing this, another error steps in, which is the round-off error, which means that if you're going to use this 10 to the power minus 4, you better use a lot of significant figures after your decimal point, okay? Which can be also intuitive at the same time, if you think about it for a moment, which I can repeat this again, which means that you go deeper into using smaller delta x's, but be aware that you have some round-off errors for a lot of quantities that you are using, unless you are using integer values, which are the only numbers which you can define with infinite precision. The 5, it has infinite precision. Any other number, irrational numbers, they are not. Irrational numbers, they are defined like square root of 3, square root of 2, or any number that cannot be written as 7/5, which is the ratio of two integers. Let's move on. So topics that we are going to discuss is going to be the root finding, and then we'll step after the root finding, we'll cover some solution of linear systems. But allow me to go directly to the root finding steps. So here you can see the slides even later. I suggest to read chapter 2 and chapter 3. It tries to teach some skills in MATLAB, the programming language that the book is using mainly. And MATLAB is a relatively widely used programming language for engineering. And now here there is some discussion or some comparing what is accuracy and precision. So here in this graph, actually, you can see that being precise, it means that you are precise within your own data set, but you are not precise with the true values. Okay, so one person to be precise, an individual to be precise, this means that he is coherent with himself, so to say, but not with the result. But being accurate, what does accurate mean? It means that the average of the overall measurement is the exact value. Whereas the being precise, that means that, oh, maybe I can better say it in this way. Being precise, it means that you have a small standard deviation in your measurements, okay? So being precise, you are decreasing the standard deviation, but you are wrong in the average that you measure. So probably we can, but on the other way, being accurate, that means that your average measurement is correct, but you have a huge standard deviation. Now, the average value that you measure and the standard deviation, I can show this later when I switch to showing the board. This is going to be, there are the moments, whenever you have a data, the data has the first moment, second moment, third moment, fourth moment, and what these moments mean, assume that you are given 5 measurements. Randomly generate some 5 measurements, and one of the moments is the average value. The second moment is the standard deviation of the data. The third moment is the skewness. The fourth moment is the kurtosis. And all of these parameters that I just mentioned, they're just quantitative measures which describe to anyone the shape of the histogram of a data set. And the concept, to have it clear, the concept of histograms is very important. And so what I said here, what we can see here in the definition of the accuracy and precision, the idea of the average value and the standard deviation is enough to understand what is going on. We can go next with, okay, so let's move on into the root finding. So when we're talking about this, we have two major approaches. One of the approaches is the bracketing method, and the other one is open method. What the bracketing method means, this means that you know that you have a root. You have a root in some given range, and you are going to search in that range, which is something good to know. Okay, and then but in an open method, you don't know the bracket, you have not bracketed where the solution is, and you try to approach to the correct method by using computationally efficient algorithms. And for this one, in the bracketed method, one of the methods is called the bisection method, the other one is the false position method. There are also a couple more, but it's not worth covering all of them, but rather getting the general idea, and we can always develop or understand other simpler or more complex algorithms. Then in the open methods, we start with discussing the fixed point iteration method, Newton-Raphson method, second method, and we have also a couple more, but let's move on. So there is also a hybrid approach, which is a brand root finding method, which includes bracketing and smart algorithms similar to Newton-Raphson methods. Now, let's see what the bracketing methods is. Now, whenever we start with bracketing methods, we can always try to graph the function that we want to zero in, or that we try to find the root. We just roughly draw it, and if we draw it, for example, as what we see in this graph, it looks like we have a function that has a root somewhere between 100 and 150. So this gives us a rough estimate of what the function is. So here we have a better drawing, and let me repeat it again. When we find the root, we're trying to find the x for which f of x is equal to 0. Okay, so that's what we're trying to do. So finding zeros, I think here in this slide we can also see it. We said it. We're trying to find what is when f of x is equal to 0. Now here, let's assume that we have a function. So there is a function which is shown in this graph. This example is taken from the textbook. You can also try to draw this one. And if you draw it, you see that the f of p, this function, as a function of the x-axis, is shown as in here, where we have a 0 somewhere for more than 150. Now, graphical methods, they help us to understand, because if we draw them, we are always, so if we have a graph where four different or few of different combinations can be shown in this slide, we are always trying to find when this curve intersects the x-axis, the horizontal axis. And so XL, XU, there are some, you're going to see this XL, XU. This means that X lower, X upper, which means that X upper is larger than XL, which means in the increasing values of X. So for example, well, the general idea that we see in the graphical methods, or whenever we write an algorithm, is the following. So if we have a function, and if this function is positive at some values of X, and negative at some values of x, this indicates that there could be a root between these two values of x. Because if a function is positive once, and then if you progress in one direction, it becomes negative, that means that we could have a root. But this is, I think it's clear to all of us that this would be true only if the function is continuous. Okay? If the function is not continuous, we cannot always say this, so we have to be a little careful. And so, for example, here we see that the figure on the left side, we see that the function is positive, it becomes negative. So we might assume that we have a root somewhere, but this does not always mean that we have a single root. We can have more than one. Now let's move. So this is bracketing methods. You can see it here. It always works, but it converges slowly. And the level of convergence. Now you are second year in computer engineering, and one thing that we are really scared about is exponentially increasing functions. We're not that scary of exponentially decreasing functions because they will converge to 0. It's a nice region we are comfortable with. But anything increasing too fast, that means that it's something that we cannot handle. But it's good for us if things exponentially decrease, because that means that we can converge to some value. And in this case, what is relevant with the bracketing method is that one of the best methods for bracketing is that we can determine a bracket, a range where the solution is, and we can keep dividing this given range by 2 each time. And once you keep dividing by 2, the next interval, it will be now delta x divided by 2 to the power n. So if you increase n, relatively fast. I mean, if you increase n, you are sure that you're going to get some good readout or some more precise in the x-axis. Now, before we do the bracketing method, in order to determine a bracket, what we can do is that we can use incremental search method. Incremental search method, what this in principle is, let's assume that you have a function that goes from 1 to 10, and we want to find the roots. The simplest thing you can try to do is that you can get this function evaluated at 1, evaluated at 2, evaluated at 3, and keep track of whether the function is changing sign. So if it's positive, see if it's, whenever it becomes negative, you are sure that you have a candidate region to have a root over there. Okay? So that's what incremental search method is. It's a very straightforward technique. You can have steps of 10, steps of 1, whatever. And you are searching for the change in the sign. Now, let's see, sorry, this is a redundant couple of slides. We're repeating the same thing. Now, let's see here a function which is incremental search method, where we have to look for roots of a function which is sine of 10x plus cosine of 3x. Now, sine 10x and cosine 3x, there are two functions that are orthogonal with respect to each other. And with an orthogonal, we're going to see it in the future, in the future weeks, what it really means. But we can assume that you have two oscillatory functions that have different frequencies. So the sine 10x most probably has a higher frequency, the cosine 3x is lower one, but they are interchangeably. They are going to scan a range between +2 -2. Okay, they're going to be +2 -2 because sine is +-1, cosine is also +1 -1. So as we can see from this figure, that's what we see. And now the thing is that when we're trying to do this incremental search, we can, as shown in this graph, if we have step sizes which are large, one can identify, let's say, 5 different brackets. And what we see here, let me try to observe here what we get. Here, reconnect, incremental search. So what we can test here. So here we have a simple code, which what it does, it tries to identify where we have a sign change in a specific function. Now let me try to incremental search. It's and we need to
break.
Okay, so as you can see from here, the code that we have here, as I said, it was just stepping. You are given a range where, I hope you are seeing the screen. So in this line of code, we're asking the program to find for possible brackets where the function changes sign between x3 and x6. So that's what we are trying to identify. Let me see if I have these functions here. No. Okay, so here, this is the function that it's also in the slide. So if we plot it, this is how it looks like. And the range is from 3 to 6. This figure that we see here is from 3 to 6. And if we search with coarse step sizes, it looks like we have 3 brackets, which means that we could have a root between 3.24 to 3.30. We could have another root between 3.3 and 3.36. And this is how it goes. Now, at the same time, if we have much better, if we refine this one a little more, so
break.
In the previous case, using a coarse step size, we figured out that we have 5 brackets, 5 candidate regions to have a root. But if you make finer steps or smaller steps in the search, in the incremental search method, we observe that we can have nine different ranges, 9 different ranges where you can have a root. Now, this is how the incremental search method can go. So here we see that if we use 60 different step sizes between the 3 and the 6, we get 7 candidate brackets, and the ranges are given here. If we give more finer step sizes, so this 1,500, this means that we can get 1,500 data points between the range of 3 and 6. Once we get this incremental search method, we find those regions. We can use the bisection method. Bisection method, what it is, it tries to, these brackets that we determine using the incremental search method, we can start and refine them by getting smaller and smaller ranges. Now, in order to identify it, what probably at this moment I could just switch to the board. Watch me here. So probably it's a lot intuitive for sure. So the bisection method, what it's trying to do is the following. So if we
Poți advertire.
So here we have two values of x lower and x upper, and here the function is smaller than 0, and this is a bracket that is given to us. Here this is larger than 0, it's positive, here it's negative, and the bisection method, what it does, it tries to identify a new value for x new, which is equal to x lower plus x upper divided by 2. So this is equal to delta.
You show him, да.
Any question? Okay, so this is new value, which in principle is going to be, it can be somewhere like here. Then we evaluate this function. What is the value of the function x at xn? We have a look at it, and it looks like it's a positive value. Given that this is a positive value, we want to pair this one with the previous last point where the function was not positive but negative, which means that we're going to check now this point and this point, because these are the closest, the latest two x values that are used to keep track of a change in sign of the function. Then what we do here, we say that this xl plus xn divided by 2, we try to identify another point, which let's say this is going to be xnn, the new value, and then we try to evaluate the value of this function. This looks like to be negative. If this is negative, we're going to pair this one with the last point in x-axis, which was positive. So it looks like we're going to search in this range, and if we started with this delta x dividing by 2 each time, this allows us to get, so if delta x is the initial step size, if we divide this one by 2 to the power n, we can determine the lowest accuracy that we want from our when we try to solve the system. And always, whenever we're trying to determine the root, we have to identify a stopping criterion. Stopping criterion, it's some value which you agree to have the correct solution. This stopping criteria is going to be some number like 10 to the power minus 4, 10 to the power minus 6, which is some epsilon, okay, some infinitesimally small value. Now, let's switch back to the screen. Okay, so this is how we move on with the bisection method, and it's just a search technique or a fast search technique where we search for changes in the sign of a specific function. Then, whenever we're trying to find the bisection technique, it's good to keep track of the errors because we always have errors. And we have two types of errors which you need to be aware of, which is the approximate error and the true error. Now, in the figure here, for one specific example, we have shown that the approximate error, it is found as the error between two subsequent iterative results, whereas the true error, it always compares the iterative values that we do find, we always compare them with the true value, and that determines the true percent error. But the EA, this would be the approximate one. As you can see from here, the true error, it can oscillate, which means that it can increase and decrease, whereas the approximate error, it has a trend of always decreasing. So you might see this one in other examples, but have a look at this graph, try to remember this, and just to see that if something oscillating, probably you are dealing with a true error. And here, there is also this that I tried to draw on the board, where the error, the first error is going to be delta x divided by 2. The nth error is going to be delta x 0 divided by 2 to the power n. And in this way, if you have some error that you might accept depending on the importance of the precision that you need in your calculation. So let's say for some applications, an error of 10 to the power minus 5 is acceptable. For some more sensitive applications, the 10 to the power minus 8 might be the requirement. And in this case, what one might need to do, one might need to calculate how many steps one is going to consider in the algorithm. This would be something like delta x, if the initial delta x is like 0.1, 10 to the power minus 1, you divide it by 10 to the power minus 6, if that's the required precision. Then this means 10 to the power minus 1 divided by 10 to the power minus 6, you get 10 to the power plus 5. 10 to the power plus 5, you take the log of this one, the logarithm of this one, log base 2 of 10 to the power minus 5. If it was log 10, it would be 5. You divide this by log 10 of 2, and you can figure out how many steps you might need to use. Now, this was the bisection method. Now, another method that can be used for root finding is a false position. And in the false position, what this includes, it tries to determine a new. So in the previous example, what we had this x lower and x upper, and the new candidate to be the root, it was the mid distance between these 2 points. But now, with the false position, we draw a straight line between the 2 values of the function, and whenever the intersection with the x-axis, we consider it as the new candidate to be a root, which in this case, as is shown here, this is xr is denoted. It's equal to x upper minus f of xu times xl, x lower minus x upper. You can see the formula. It's easy to derive. It's just you can use the similarity of the triangles that you can see in the figure. So over there, you can assume the following. What is the tangent of the small angle that you see in those 2 triangles that have these dashed lines? You know that the tangent is always equal to the opposite side divided by the adjacent side, which in this case it will be the delta y over delta x. If you write these, you can find that xr is the unknown, and it can be found as a function of fxl and xu. So this is the false position method, and this graph, we have this exercise, or this example, where the function is 3x plus sine x minus e to the power x, and whenever you see this e to the power x, it looks like e to the power x, it's the leading term in meaning that is a function or the piece of function that is going to govern the behavior of the whole function, because 3x is a linear function. Linear functions are not that extreme when we change the values of x. Sin x is an oscillating function. This is going to provide some modulations, especially at small values of x, because it's just something which goes just between +1 -1. But e to the power x is a large function, but minus e to the power x it means that this is going to be a function which is going to decrease overall. So if we try to graph this one to get a rough estimate, I plotted this graph from -2 to +2, and that's what we see. All of us, we can observe where the 0 is. Then we can replot this one from 0 to 2. We get a better approximate value where the root could be, as you can see in the second graph. And then if we use, so far, we learned two different techniques, which was a bisection and a false position. The bisection, it was just cutting in half the candidate solution. The false position, it had a more complex formula. It was not complex, but it was, you were finding the intersection of a straight line. But now, since we are at this figure, let me just ask you one thing. So the line in blue, it's the function, how the function behaves. Now you have connected, we have connected these two points of function with a straight line. Now a straight line, it would be like a fitting for linear expressions. But this function is not a linear one. So think for a moment, what could be if we don't connect these two endpoints with a straight line, with a linear function, but rather if we connect them with some quadratic function, okay, which a linear function it expresses y is equal to ax plus b, but the quadratic function, you know that it's going to be an expression similar to ax squared plus bx plus c. So probably things could get better if we draw a quadratic function, not a linear one, between these two endpoints. One thing that some of you might immediately ask is the following. How can you determine a quadratic function if you have only 2 points? But again, but because there is another method that uses quadratic polynomials between a given range. That's why I mention it now, so that you can get ready for it. Now, if we use these two techniques, the bisection and the false position, what we notice is that we can try to determine the errors, and it looks like with four iterations for the false position method, we get an error of 0.3% or 0.03%. So I guess even with a calculator, with pen and paper, in an exam environment, one can relatively easily, with 3 steps, by calculating 3 x new values for the function, one can get 0.3% of the error, which is really relatively good. But if you see the bisection method, it looks like you need an approximately 1, 2, 3, 4, 5, 6, 7, like 12 steps to get an approximate error rate of 0.2%. So what you do in 3 steps with false position, the bisection, it takes like 4 times more effort. So if you have any question, you can always stop me, and we can move. And then let me try to tell you what these are actually. So the first column is the values of x. So is the root. So that's what we are trying to find. And the next column is the value of the function. So as these numbers approach to 0, that means that we are getting closer to the root that we are looking for. Now these were bracketing methods. Now we have other methods which are open methods, and they require only a single value, unlike using 2 different values which define the bracket. Now these roots, they suffer from the problem that sometimes they might diverge away from the true root, so that we are trying to find. But when they converge much faster, but they have this little risk in bullet point 2. Now, here we're just trying to show, for example, in this figure, the figure A is used for bisection method, and the bisection method is clearly to say that once you know that you have the root over there, just take some time, you're going to find it. That's figure A. But when it comes for figure B and C, They are open methods. The B, it's let's say the way to read the figure B is the following. You are given these are iterative techniques, which means that you have an estimate for the root. It could be xi, and the next subsequent candidate for the root, which you hope to be better than the previous one, is going to be xi plus 1. Now here, this technique is Newton-Raphson that is used. We're going to see it after a couple of slides. But you can see that from xi, in figure B, if you go to xi plus 1, that means that it's not going to converge, it's not a good sign. But if you have a different function or a different, which is not exactly like that one, if we can get from xi to xi plus 1, that means that we are getting closer to the root. So this is just a graphical depiction of how open methods can converge or diverge. Now, here, one of the first techniques that you can use among the open methods is called the simple fixed point iteration, which we can call it FPI, like FPI. Okay, I have to stress the P. It's not FPI. It's fixed point iteration. So let's not use acronyms here. Yeah. So here, I think the bottom part of the slide is that we're trying to identify cases for which, or x's for which fx is equal to 0. And what we need to do here is that we can add x to both sides of the equation. Then all of us, we can easily see that x will be f of x plus x. And the idea to write it in this way is that we want to write x as a function of xi. So we want to construct a relationship between an iterative relationship between the values of x, assuming or hoping that xi plus 1 is a better root than xi, than the previous one. So I think in the end you can see that we're trying to artificially try to construct a relation of x as a function of itself. So the approximate error, if we don't know the true error, the approximate value, it will be written as xi plus 1 minus xi over xi plus 1, assuming always that the new value is better than the previous one. So always when we calculate the error, we try to find the absolute value of what we find with respect to the true value, and then we would divide by the true value if this was the case. But if we were talking about approximate error, instead of the true value, we always put the latest value. Sometimes students try to do this in the homeworks or in the assignments, taking as a reference the previous value. We don't do that. The reference, or assuming that it's a better value, is the latest one. So this is how we calculate the error. Then here we have one example, which is e to the power minus x minus x. This is the function. So the function here that we give, this was e to the power minus x minus x. Just for a moment, I can switch to the board just to. So the function was. So we are trying to find the root of what was the function e to the power minus x minus x. So this is what we are trying to find the root of, and then all we do, so we are trying to get when this is equal to 0. Okay, let's not forget this. So all we can do, we have here 0 is equal to e to the power minus x minus x. Let's add from the both sides of the equation plus x. So, and then here we get that x is equal to e to the power minus x. So then this is what we try to, from this function, this is what we get. I think it was easy to figure this out. This is equal to g of x. So we say that xi plus 1 is equal to a function g of xi, which in this case is just simply going to be e to the power minus xi. And then, so this is how we're trying to find the root. And we can start by first, we can have a rough estimate. We can assume that x initially is equal to 0. So let I be the first iteration. And let iteration 1. What is x? X is 0. If this is xi plus 1 is going to be the next value. Xi plus 1, let's look at the expression. It's going to be e to the power 0. E to the power 0 is 1. Okay. So it looks like for this function, e to the power x, actually what is e to the power x minus x? What would this be? We know what e to the power x, no, this is e to the power minus x. Here we have 1, and if this is a 1, e to the power minus x is a function of this. It's always good to have an approximate estimate of what's going on. And we have to subtract minus x. So minus x as a function is this. So if we add these two, it looks like we're going to get something like, of course, with modifications, it's going to be a function that looks like this. Okay, so probably you can do a better job than me, but this is, and then we're trying to find 0 here. And then, so this was, the initial root was assumed to be 0, then we got the 1, then we go to the second iteration. So we say, what is the xi here? It's 1. Then the next value, so x0, it was 0, then x1 is going to 1, then x2 is going to be e to the power minus 1. Okay, e to the power minus 1, it's 1 over e, so 1 over e is something like 2.72, so we get a value of around 0.3536. 0.36, so x2 makes this 0.36. So in the next iteration, in iteration for I3, this is going to be 0.36. The question mark here is that x3, the next iteration is going to be e to the power minus 0.36. And the value that we get for this one is something around 0.69. 0.69. And meanwhile, if we are trying to find the errors between these, the approximate error, we find that, for example, the error that we have in this first stage is going to be equal to, so from 0 we found 1, or from 1 we found 0.36. So the error in this stage is going to be 1, absolute value, 1 minus 0.36. divided by 0.36, because this is assumed to be better, times 100%. Okay. This is going to be give us a specific value for the error. The next error, which relates this step, is 0.69 minus 0.36 divided by 0.69, because this is closer to like true value, times 100%. So this is how we move on and try to identify these. The next iteration, of course, is going to be 0.69, and e to the power minus 0.69, we get something like 0.5. So this is how this is going to progress to find the. So this is how we do the steps. I strongly suggest you to go over these, following also the examples in the book, in the textbook. So if we do these, we see that this is how. Give me a second. This is how we find the first column. It shows the roots. So x, we started with 0. The next value, it goes to 0.36, 0.69. But it looks like after some, if you look at the bottom part of the first column, it looks like 0.564, 0.568, 0.566. It looks like we're converging somewhere. And we can switch to the third column and have a look. And in the third column, we see that the errors are also decreasing. The errors are in the order of 1% or less than 1%, like 0.6 or 0.35%. There's the same thing for the approximate error and for the true error. Now, to calculate the true error, we need to know the exact root. The exact root for this example, it's 0.56714. Okay. So we use the fixed value to find the true error, and we use the two subsequent values of x to find the approximate error. And in order to study the convergence, because whenever we do these algorithms, the analysis of the convergence, how fast one is approaching to the true value or not, we can calculate the two subsequent errors. If you see the final column on the very right side, we see that we get an almost constant value. Now, whenever we get this And this one, now assume for a moment you are saying that ei plus 1 is equal to a constant c times ei. This means a linear dependence, which means that the same way that you say that y is equal to 2x, if you draw this graph, it's a straight line where 2 is a slope. Now, in this case, the subsequent error that you can see in the ET, you can see that you can write that the next error is always half of the previous one. So even the error we are bisecting, we are dividing by 2. This is called a linear convergence. And the term linear convergence is just saying that the next error is a linear dependence on the previous one. We have better converging algorithms where they converge much faster, which are not linear convergence but quadratic convergence. We see these cases. Now, this is linear convergence. So fixed point iteration is linear convergence, as seen in the previous slide. And then, now there is something important here, because we saw that the x was written as a function of g. Now, this fixed point iteration, it does not always converge. The reason is that it depends on how this function g of x behave. And if you take this g prime, it means the derivative or the slope. And you know how the slope is? The slope is just simply stated is a tangent line to any point on the curve. So let's, in the next slide, we just see that. So I think that's what we need to look at. And here we can also see that the next error in the iterative steps to find the new root, it can be expressed for FPI as the derivative of the function g at this value psi, the Greek letter. It means that these values of x, which we continue to try to find. Now here we depict for the fixed point iteration technique. Here there are 4 different scenarios where the top 2 ones, they are converging, and the bottom 2, they are diverging. In one word, which might make things way simpler, is to compare the slope of the function of g of x with respect to the function y x is equal to y, which is a straight line with an angle of 45 degrees with respect to the horizontal axis. And it's just showing that if the absolute value of the slope is smaller than 1, that means that for any function that hovers around between the x-axis and the y is equal to x line, all of these functions, they're going to converge. But if the function, it's a steep curve, okay, with a high tangent, or with a high, what can I use here, slope. If the slope is huge, then this fixed point iteration, this does not converge. Okay? So as you can see here, if you follow whatever the function gives, you are, rather than approaching to the root, you are diverging. One little thing that you have to consider here is that the root is going to be where the x is equal to g of x, okay? So if you are trying to find the root of the f of x, notice that in this graph, f of x is not shown, but you know that whenever the x is equal to g of x, that's where the f of x is equal to 0, depending on what we said a couple of slides before. Now we go to another technique, which is very commonly, you see this a lot, so you might so I'm not saying that you're going to forget this, but Newton-Raphson method should be the last method that you should forget, or that you could forget. Unless you have a friend that is called Brent, or is called some other technique, but Newton-Raphson method should be the last one that you should remember. It's simple, it's fast, it's one of the cons is that it's not always used, because this works for functions that the derivative can be determined. Now, it can be tackled graphically and using the Taylor series expansion. The reason that we can use Taylor series expansion is that this Taylor series expansion, it includes the derivatives. Now, the formula for the Newton-Raphson, I can really ask all of you to write down the Taylor series expansion as we did in the examples that you can see also in the video that was posted this week. Write the Taylor series expansion and just take the first 2 terms, okay? That's it. So if you take just the first 2 terms, you can notice how, so let's see what we get here. In the Newton-Raphson method, the formula that is very useful is this xi plus 1, which is going to be equal to xi minus f of xi over the derivative of f of evaluated at xi. As I said, it's very simple, easy to derive. You just need, if you have a look at this, write the Taylor series expression, or look at this graph, draw the slope at xi, and try to see where the slope is going to intersect the x-axis. Okay, so that's the general idea. The error, it progresses in a much nicer way, because the error, it's the subsequent error is the square of the previous values. So assume now you are drawing, when you calculate the error for the FPI, you are drawing a graph which was y is equal to x. Now you are drawing a graph which is y is equal to x squared. And this is called the quadratic convergence for the simple reason. And the quadratic convergence is way better than linear one. And now, let's see this example that we solved before a while using the fixed point iteration, which was e to the power minus x minus x. Now, the subsequent values of x, we find them with the formula, the first formula shown in the top. And if the function is f e to the power minus x, its derivative is going to be the second equation here, which is easy for you for all of us to understand it. And the next subsequent, the relationship between any two subsequent values of x, which are candidates for the root of the function, for the value for which the function equals to 0, these will be written in such a form. Now, the same problem that we solved, that we had a lot of steps before 3 or 4 slides, it took a lot of time, but using Raphson method, we see that using an initial value for xi of 0, in 2 steps, we get an error rate of 0.1%, which is really good. Which means that, or which proves that this Raphson is much faster in convergence than this. You see how many steps we needed here? I can count probably 12 to 15. But the Raphson, in 2 steps, you get an error of 0.1%, which is really good. Now here we have another example for Raphson method, which is the function is e to the power x minus tangent x. All we need to know, what we need to find right away is that what is the derivative of this function? E to the power x is e to the power x. What is the derivative of tangent? Is secant square, secant square. You can write a simple code about this. You can let me have a look here. So let me, if I share the screen, so if we can move around here. Click here to reconnect, just to I'm sure you can all try all of these. So we have this Raphson method, and this is the example that we had in the previous slide. I have, what is something important in all of these root finding techniques is this line of code which determines what is the stopping criterion. So where, if you want to make this function f equal to 0, is it good enough for you to not to be exactly 0, but something like 10 to the power minus 5, which is 0.0001? So that's what we can use here. And let's see what, so if we run this, the output here, the function itself is exponential minus e to the power x minus tangent x. We are deriving by the derivative. I think this was clear. We're trying to have an iterative schema here to see and searching for the stopping criteria in line 6 of the code. What we get, it looks like the root is 1.3. Okay, the root is 1.3. How many iterations did we need to go? Instead of doing 1,000 steps, apparently just 8 steps was enough. So that's what we see here. If we have a stopping criteria, a little finer stopping criteria, let's make this 10 to the power minus 7 and save this. Instead of 8 steps, oh, it's still 8 steps. Okay, so it looks like with you see, from 10 to the power minus 5 to 10 to the power minus 7, we still have 8 steps. Let's make this 10 to the power minus 2. Let's see if we get any difference. No, it's gone 7. Okay, just so it looks like even this initial value, let's make this back 10 to the power minus 7. But if the initial guess, which we set it as 1, let's set it's 144. Okay, let's try to be far away from a root which it should be 1.3. Okay, so we should find this. Let's see what we get. It looks like from 7 iterative steps to run this little search algorithm, searching for the value of x decreasing, getting close to 0. Starting with an initial guess of 44, we need 40 steps apparently. 40 steps. If we make this 40, if we make this 10 to the power minus 9, if you want to make this a little finer, it's still 40. Okay, actually it's still 40 because if you see here
9.4247.
Okay, so the f of c, you can see here. I think last time we had a lecture in the class, we observed that machines or computers or any programmable unit, it has its own epsilon or its own epsilon. It looks like this f of c that we have found here for the last couple of examples. They are all epsilons because they are 10 to the power minus 16. Okay, so this was just how one can simply write this short piece of code to find, using the Newton-Raphson method, to find the root of a specific function. Now, let's move on. So this was one example. It looks like with a j equal to 3, with 3 iterations, we could find the root. Now, to see the graph, there are some examples for which the Newton-Raphson method is not very fast, this is one of the examples here. So you can try. So this code is here on the slide. You can try to run this on your own. What I was running before a while, rather than using the commercial version of MATLAB, you can always try to use the free version, which is the Octave. And here we see some difficulties of the Newton-Raphson method and difficulties of the Newton-Raphson method. When you see
break.
Sorry?
Can we make a short break?
Yeah, actually we could, and probably we're going to have it relatively fast. But can I have a look at what the slides tell? For the moment, now let me say also this. In this way that we're covering the lectures, I think we have to be a little more active in terms of the connections, or at least communicating through emails or other means. And with this one, I mean that even for this chapter of root finding, which is chapter 5 on the textbook, we're going to have another sections where we're going to cover the questions that you might have, or also I can solve some examples. Next year's very small reminder is that this is recorded. You can always go back and have a look at those. And another thing is that we're going over the slides, which you already have them, and I hope they can help you. We can have the break, but I can also add that if we have the break, right now I'm at the university, which means that I might have to leave before 1 p.m., before the class is over. So, but let me have a look, allow me to have a look at what the slides, the rest of the slides. So, if you give me another 5 minutes, I think I can give the essence of what the future slides are about, and I can get some of your questions. So now, as I said, Newton-Raphson method should be the last method that you might forget regarding this course. The other ones are because it's really an important one, and there is some problem with it. The problem is that you can always, not every function is differentiable. Okay, if you approach to some specific values, you know that some functions might explode, might increase too fast, and for that one, we may determine using numerical techniques. We can find the derivative using different techniques, and all the methods that we are going to talk from now on, especially the second method, all it does, it defines the derivative of the function differently. So the Newton-Raphson method, it inserts this function that we see here. We have, this is called the second method, second, and there is also a modified second, which is just two different ways of writing or defining the determinant. Now, this is an example of a second method. Here we have the inverse quadratic interpolation. I think you do remember this FPI technique, which was trying to draw a straight line between two candidates, between 2 points of the function f of y. Now, the inverse quadratic interpolation, which I'm not going to talk too much, at least for now, it is something that you saw before, but you are not drawing a line which is going to intersect with the x-axis, but you're going to draw a parabola or a quadratic parabola, and then trying to find a candidate new root at the intersection of that line. Now, I can ask you, do you have any question for what we talked so far. Any question? Let me see. In the platform, do you see this chat section where you can chat or you can write comments or something? Let me see. Actually, I should be. Yes, that's good. So far, I just see some of you confirming that you are online. But if you have messages, you can write. You can write questions here. So. And in today or tomorrow, I'm going to post an assignment regarding this topic that we covered. Okay, so we have no question. How many chapters should we read? Okay, that's a good question. How many chapters from the book should we read? You mentioned chapter 5. Chapter 5 is the root finding chapter, which is according in the Chapter textbook. But I don't remember. I don't have the. Let me have a look if I can find the. Because I don't have the book with me, but in turn, this textbook is very. I'm trying to find the outline of the textbook. Okay. So the chapters that you're going to see, I found something that I can refer to. So, okay. So chapter 5 is root finding. So today we went over actually chapter 5 and chapter 6. So go over chapter 5 and 6. Okay, that's a good question, Ergus. Ergus, can you show some effort on your own? We can do it. Yes, we can do it. So the book, it's how can I say? I posted it's in the syllabus, online version of the syllabus, where the textbook and the author and the publishing house and the edition are posted. So, but I can put it again, all the information regarding the textbook, the information on the textbook. So I said chapter 5, 6. Then we'll do chapter 9, 10. Let me go over these iterative methods. 11, 12. But I mean, rather than telling all of them right now, yeah, this is the sound, the tone everybody misses, the Nokia tone. Okay, so I'm very happy to hear it again. It's the exact title, Professor. Oh, okay, the exact title. Yes, the exact title. That's you know. Let me get this. The exact title. Just give me 1 second. It's applied numerical methods with MATLAB something. Let me get it. Yes, I'm going to write it just in a second. This book yes, that's correct actually. There are, I mean, numerical methods, numerical techniques, it's very, I found it. Numerical methods for engineers. Now, the addition is not that important because maybe from one edition to another, not too much change. But yeah, I think anything from the 3rd edition is really it's enough. Any other question? I guess you can also ask questions by sound. I mean, using your microphone. That's what I mean. Okay, nothing. Okay, then I guess if you don't have any more questions, I guess we can close this session for today. And but I can also welcome your questions by email or even this platform here that we have, this also offers the opportunity for comments or questions. Okay. Okay, so for another minute, I can wait for possible questions. Otherwise, we can stop this session. What is this? Okay. Yes, some of your friends are posting helpful material, which you can refer to or you can have a look at. And at least the PowerPoint slides that they are posted here, you are encouraged to go over those. Yes. Okay. The outline. Okay, that's a good thing. So the outline of what we covered today, it was that we try to, and I guess we can stop sharing. So what we did today, it's always good to. So we cover the topic of root finding, and root finding, we have the closed method, which means that there are methods where you bracket the root, and then we have also open method. Open method are the ones that don't bracket the root, but where Newton-Raphson was one of them, NR, Newton-Raphson method. And we looked at how we can find the root, and root finding in principle is, the question can be posed like this: x is equal to what, such that f of x is equal to 0. Okay, so that's what we are trying to determine. And when we are trying to do this, we're always using iterative techniques. We're always trying to find for which value of x f of x is convergent to 0 faster. And during all of these steps that we use, or during the techniques that we learn, we always try to determine the error, and the error, it was equal to xi plus 1 minus xi over xi plus 1 times 100%. And this gives a percent error, the approximate percent error for this for the root finding. Now we covered different approaches. We analyzed also the convergence. We analyzed the convergence, and the convergence we saw a couple of examples. So if the error, the next error, it can be written as a constant times the previous error, we call this one a linear convergence. This is linear. But if the errors are related to each other, like if the error of I plus 1 is equal to any constant c, that's ei squared, this is called quadratic convergence. And this converges much faster. So the second one, where Newton-Raphson method is one of those, but the linear convergence, the fixed point iteration, this is a linear convergence technique. The NR, the Newton-Raphson method, this is a quadratically conversion technique. So that's what we saw. Other than this, then I made a small note when we were discussing about which I feel is a little important, when we discussed about the precision and accuracy. We said that whenever we have some data, when we say data, we say the following. So we have a measurement when x can be equal to 1.1, 2.3, 4.7, 8.7, 11. So assume that we have some data. All of these data we have predetermined. So all we care about the data is to have a description of how they behave. And in the analysis of this data, these are called the moments of the data. With moments, the first moment is the average. So the first thing that one is interested about this type of data is the average, x average, which is going to be equal to the xi divided by n. This is the first moment. Then the next important parameter is the standard deviation. Standard deviation is something like a sigma, which is going to be equal to this xi minus x average. So this value that we found here, this is squared divided by n minus 1. We have to sum here. This is called a sigma, the standard deviation. Now, the reason I wanted to mention this is that we said that if this is a true value, so let's assume that we have a value and the true value is here. Now, this is the x0, this is the first moment, and this is the sigma, the standard deviation, or the width of the histogram, or the width of the distribution. These are two important parameters which tell us how a certain measurement behaves. And the thing is that when we had the discussion of accuracy versus precision, we noticed that accuracy it focuses on x0, okay? Accuracy cares to get the average of all the measurements to be correct. But precision, not that it cares about sigma, but precision has a much more small sigma. So if someone is always shifting the measurements by some specific values, but all of the measurements have a small standard deviation, that means that he has a high precision, but has a low accuracy if the average is shifted from the true value, let's say. So have a look at this representation here, and have a look also at the slide where we are trying to show to compare what accuracy and precision is. So more or less, this is what we did today. So let me have a look if we have any further question. Oh, is the video quality bad? Okay, so sorry about that. Now, regarding the video quality, let me see. Stop settings. Because I should have asked you about regarding the video quality, and let me try to. Okay, it looks like I'm a little bit restricted in fixing this right now, but of course I can take I can provide this one in the slides. Okay, what I've written in the board. No, quality is fine. Okay, so we have some comments about this one. Let me check. So I'll just attempt one final thing, which would be I can improve a little bit the quality that I'm streaming out. Did the resolution improve something? Does the quality look any better, or anyway? There was this setting. Okay, I can take a quality is fine, not yet. Okay, if you don't have any more questions, we can. It's better now. Okay, so we have our. Thank you, Aniledio. Yeah, there was this option where we could slightly improve it. Okay. The next meeting, you might expect this one. Most probably, I want to hold around Thursday, okay, this week Thursday. But I hope you can. I can send an email, but let me think about this one for a day, okay, regarding the next meeting. But I want to have it on Thursday. Everything you'll be notified before, at least one day before we hold the class, okay. Okay, then. Yeah, thanks, Katie, for the question. Okay, so then I hope you all do fine. I guess I'm gonna close this session and see you next time. Bye. Bye. Bye.